Saxon Advanced Mathematics, lesson 32. I hope you're in the right place because we have got a fascinating conversation planned for today. I mean, let's face it, it's a monologue. You don't get to talk as much as I do, but you know what? If you want to talk, feel free. We're going to talk first about inverse functions, and then we're going to talk about inverse trig functions. All right, so we're just going to do general conversation first, and then we'll get into the specifics of how this relates to trig functions. Let me remind you of just kind of a really simple way that we can understand functions. It's called a function machine. You know what I'm saying? We've drawn things like this before. We take some numbers, and I'm choosing 2, 4, and 6, and those are our independent variables, those are our inputs, those are our domain. We've got lots of fancy words. And then we have a very simple function, 2x minus 1. We also consider these our x values, right? This is x. And this over here is y, right? And what we do is we take our x values one at a time and we plug them in and we calculate and we get y values that correspond, right? 2 times 2 is 4, minus 1 is 3. 4 times 2 is 8, minus 1 is 7. And 6 times 2 is 12, minus 1 is 11. So there we have it. It's a perfectly valid function. We put in each of these values, we will always get this value back, right? Everything is happy in our world. But what if, for some reason, we decided we wanted to reverse this? We wanted to start with 3, 7, and 11. Let me just draw that picture. Instead of these being our outputs or our dependent variables, what if we wanted to make those our x's? 3, 7, and 11. And we wanted to calculate some function that would allow us to take each one of those and go backwards, kind of, and get 2, 4, and 6 as our original, as our new outputs, right? We're reversing everything. These are coming over here, and these are going over there. Now, I'm going to tell you what the inverse function is, and then I'll show you how to calculate it. 1/2 x plus 1/2. 3, we put it in here, we get 3 halves plus 1 is 4 halves, and we get 2. 7, we put it in here, 7 times 1/2, that'd be 7 over 2, plus 1 is 8 over 2, and that's equal to 4. 11 halves, 12 halves, 6. All right, so we can see that it works, and we can kind of wrap our heads around the idea that we were putting in this and getting out this, but then we wanted to reverse it, and we want this to be what goes in, and we want some function that will give us the original numbers back. So how do we do, that's what an inverse function is, by the way. To calculate an inverse function, I'm squeezing. This is what we do. It's kind of weird when you write it down. And I'm going to show you how to do it so you won't be confused. All right, so to calculate an inverse function, you take the original equation and you solve it for x, right? So our original equation was y equals 2x minus 1. Right? So we might just have that part of it written in the box. So we have to add the y equals sometimes, not always. All right? So we start with that. Now we're going to solve it for x. There's our x there. So let's start by adding 1 to both sides. And we'll get y plus 1 equals 2x. And then we'll divide everything by 2. And another way to write that is 1/2 y plus 1/2 equals x, right? I just kind of separated the fraction from the letter here. That's the same, and there's my plain x. That's step 1. Right? We solved the original equation for x. So x is by itself. Now we do this swapping thing. We swap x with y and y with x. And so our answer then becomes 1/2 x plus 1/2 equals y. See? I just rewrote them. Okay? And if we want to write this in the more familiar form, we write y equals 1/2 x plus 1/2. And we see that's exactly what we got here. I told it to you here, but we checked it and we made sure that all of these really did equal. And now I just showed you how to actually calculate it. This is our step 2 right here. That's where we switch it out. Okay? So what we're going to do is apply this lovely knowledge that we have just gained in, I think it's just 2 problems, and then we'll switch to talking about inverse trig functions, which in some ways are a lot easier. Okay, new page. (32.1). It says, find the inverse function of y equals 2x plus 3. Okay, we just follow our 2 simple steps. 1, solve for x. And these are just shorthand versions of what I wrote on the last page. Okay, so let's see. Let's subtract the 3 from both sides. That will give us y minus 3 equals 2x. And then we'll divide everything by 2. And I like to do the terms separately rather than just show a combined number. That's usually the way we do it. And then I'll get 1/2 y. Again, I'm pulling the fraction apart and putting the variable there. Minus 3 over 2 equals x. And then step 2. Let's say swap. Swap x and y. And I'm going to bring this over. So this becomes y equals 1/2 x minus 3 over 2. And that's the correct answer. What do you know? Kind of cool, right? And we can do one more. This time we're starting with y equals minus 2x plus 5. I'm not going to write the instructions, but you can remember what to do. So let's see, we're going to add the 5. Y plus 5 equals minus 2x. We're going to divide by minus 2. I'm going to bring the x to the front now. X equals minus 1/2 y minus 5 over 2. This should be a minus 5. And this should be, so minus 5 over a, right? Because I'm subtracting this and bringing it over. So this should be a minus, and then I'm dividing it by minus 2, so it ends up being positive, right? Because the 2 negatives make a positive. Okay, and then my last step is I swap the x and the y. So I would write y equals minus 1/2 x plus 5 over 2. And that's the correct answer. Yay. All right, now I just want to show you one thing in the book. John does not ask us to graph these, but he shows us how they look, and it's kind of cool. For the first problem that we did, it doesn't really matter, you can see. If you graph the function and then the inverse function, look what happens. The equation for y equals x goes right through the middle of the two related functions, right? This was the original and this was the inverse. It always makes this cool pattern where the simple y equals x goes right down the middle. And the same thing happened here in an even weirder way, right? In our second one we did, there was our original function, and this is our inverse function. And look, we still get the y minus x, but this time it cuts through the middle there. Whoa, it's so weird, right? That's, I think it's because this one has a negative slope and this one has a positive slope. That's the difference in the way that y equals x cuts through. We're not gonna spend much time on this, but I just wanted to show it to you because it's really cool, right? Y equals x always bisects the function and its inverse. Very, very fun and cool. Okay. Enough fun and games with just general, and those were just equations of lines, right? They were just little linear functions that we dealt with. Now we're going to change the speed of our conversation here and talk a little bit about inverse trig functions. And we have already talked about these a little bit. Normally, when we have a trig function, it's like this. Let's say sine of theta degrees equals Oscar over hypotenuse, right? Let's say we don't know the angle or either of the two sides. I just want to talk about it generically. Normally, for a regular trig function, we know theta, but we don't know the fraction. We may know one part of it, but we don't know both parts of it, okay? For an inverse function, and we'll talk more about this, this is not the only time I'm going to make this point. In this one, we do know that fraction, but we don't know the angle. Okay? Sometimes this is in a decimal form. And sometimes this is in a decimal form. So I just want to point that out to you. And theta is always equal to the degrees of the angle. Okay, so I'll often talk about we know the degree, but we don't know the decimal. Or with inverse trig functions, we know the decimal and we don't know the degrees. I often use that language. Just remember that the decimal is the fraction, just written in decimal form. And also know that we have been calculating these already. To find the regular trig function, we use these buttons on the calculator. Sine, cosine, and tangent. And to find the inverse functions where we know the decimal number but we don't know the degree of the angle, we use with the little minus ones. Remember these? And you have to hit second to get them. Right? So we have done this already. We're just going to add to our knowledge. All right, so this is some backstory, what we already know about tangents. Now, I want to tell you something else before we dive too much farther into this. I want to review what we know about the signs of the quadrants, right? We know that, and I'll show you the way we memorized it. We did plus, 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 minus, plus, minus, right? We've done this in the past few lessons. We know that each trig function has a positive or negative sign. It varies by quadrant. We memorize this little device, but we remember that this is sine, cosine, tangent, and this is sine, cosine, tangent. And then over here, it's the same, right? We just kind of don't bother writing this down every time because it's fairly easy to remember. But in this, because I'm using this diagram to explain something else, I want to fill in the blanks. Okay. Now I'm stuck because I'm going to be flipping pages, right? But that's all right. Just remember this. And one thing I want to point out that's weird is that sine is positive and negative. When you compare first and fourth quadrant, sine is positive and negative. Tangent is positive and negative, but cosine is positive and positive. In order to find negative values for cosine, we need to go over here. That's going to become important later on. So keep that in mind. I'm going to talk about that in just a minute. All right? Let's now talk about the inverse cosine function. We're going to flip it over. Okay. And I'm doing cosine first for a reason, and you'll understand in a minute. So here's a fun little triangle. Let's draw a 60-degree angle in here. And that will be helpful because we know the lengths of the sides for a 60-degree triangle, right? This is the short side, and this is the side that didn't get chopped in half, and this is the square root of 3, right? So we can find that the cosine of 60 degrees is, let's see, it's adjacent and hypotenuse, right? So adjacent is 1 over the square root of 3. Okay, that's cool. So what we're saying is this is the way we normally write it, where we know the degrees and then we figure out, in this case, we don't use it in decimal form, we just leave it as a fraction. But we could turn that into a decimal. But we're going in that direction. Now, what if we were saying the cosine of some angle equals 1 over the square root of 3? And we're trying to find out which angles would have this cosine. Here's where it gets a little nutty, because this is what we're thinking about when we're thinking about inverse cosines. We're saying, tell me how many degrees would be the angle that would give us a cosine of 1 over 3. Okay, and so we go, dude, it's 60, right? But what if we went all the way around the whole circle and came back? That would be a 360-degree circle plus 60 more. So that would be a 420-degree angle. What if we started here and we went around twice and came back? Well, then we would have another angle that would still have that same ratio. It would be 720 plus 60, or a 780-degree angle. And you can see that I could keep going on and on and on and on and on, coming up with more and more outlandish angles, degree measurements, that would give me this same cosine value, because as long as they stop at this same line, I can spin around an infinite number of times, right? So this list is going to get really long, and no one wants that. We don't want that, you guys. So what we do is we place a limit. On the angles okay? We're gonna place a limit for all of them, but I'm talking specifically about the cosine now. What we're saying is we need to make sure that we have enough angles so that we can come up with every possible cosine, positive and negative, but we wanna limit it. We don't wanna allow ourselves to keep spinning. So what we do is we say, okay, we're gonna have to allow all of these first quadrant angles, because that's where all the positive ones will be. And then we're gonna need to allow, I wanna use orange for this. If we allow our answers to come from just the first and the second quadrant, remember that's how they're numbered. Let me do that. 1, 2, 3, and 4. And let me also remind you, this is 0 degrees, and this is 90, and this is 180, and this is 270. What we're gonna say is for cosine, if we just pick angles that fall between 0 degrees and 180 degrees, then we'll get the full range of all the positive and negative cosine values. We don't have to allow angles down here. We don't have to allow angles down here because we would find them up here. And we don't have to allow for all the spins. So what we do is we place a limit on this. And in a problem like this, where we're trying to find the angles, we place a limit that says theta is, and I just have to make sure I remember which one gets the equal to. I think it's the 0. I'm quite sure it's like this. Right? So what we're saying is you don't need to spin around finding all the different angles that would have this cosine of 1 over the square root of 3, which would be anything that ends at this 60-degree marker. We're limiting the choices by putting this limit on our inverse cosine calculations. All right? So this is a huge favor to us. This is our regular function, right? We know we're given this and then we answer this. And this is our inverse function. And in this one, we're given this information. We have to solve for the degree. And we don't want to have to deal with all of this. We just want to be able to give an answer like this. And that's what we do when we place this limit on it, because we're saying 420-degree angle, we don't need to know about it. 780-degree angle, we don't need to know about it. We just want one of them. All right? So that's what is a little bit tricky with our inverse functions, is that we want to limit the number of angles that we will have in our solution. We say just give us one positive and one negative, right? So for cosine, we use the first and second quadrants, and we define it as ranging from 0 to 180. Now, because of the patterns of positive and negative, sine isn't going to work if we choose the first and second quadrants as our limit. For that, we're going to choose our first and fourth quadrants. So let me just show you a little bit about how that one works. Let's use purple for sine. So for sine, what we're going to do is we're going to take all the positive angles in the first quadrant, and we're going to take all the negative angles in the fourth quadrant, and we're going to say that's our limit. So I'm going to write that up here. Here for sine, I'm writing these by these ones. It's the first and the fourth quadrant, and we'll say from 90 degrees to minus 90 degrees. Okay, so it will work just the same. Let me go back and kind of repeat all of this for inverse sine. Okay, and again, I'll use a 60-degree angle so that it's consistent with what we did last time. This is 60 degrees, this is 1, this is 2, this is square root of 3. for the regular function, we would know the degree, so we would say, find for me the sine of 60 degrees, and we would fill in the blank by saying, okay, sine is opposite over hypotenuse, so it would be square root of 3 over 2, and that would be the answer. When we go to find the inverse function, we're saying find all the angles, that's why we put the variable in there, that would have a sine of square root of 3 over 2. And this is where we start the spinning thing, right? Because we would say, okay, so theta can be equal to 60 degrees, but we could also spin around an extra time, and then it would be 360 plus 60. Again, all of these same combinations, right? It could be a 420, or we could go around twice and stop at the very same line. As long as we're still stopping at this same line, all of those different angles are going to have a sine of square root of 3 over 2. 720 plus 60 equals 780. But we don't need to know about them all. That's just ridiculous trying to list, because it goes on to infinity, right? We just keep adding 360 to 60 degrees, and it would go on forever. So what we want to do is we want to place a limit . Okay, so we're going to place another limit so that we don't have to keep spinning. But the difference is this limit is going to be in the first and the fourth quadrant. So we'll say that the theta that we're choosing, the degrees for this angle, are going to be between 0 degrees, plus 90, no, minus 90 and plus 90. That's the way we write it for sine, right? The reason it's different is because sine is positive and negative in different quadrants than cosine is. That cosine's the weirdo, all right? He has to do first and second quadrant, so his limits look a little different. All right? Did I do sine? Yeah, I did sine in purple. Okay, good. All right, so this is the kind of limit that we will use when we're talking about the inverse of sine. All right, and then we just have to talk about the inverse. Oh, I know, I wanted to say one more thing about this though, and I didn't say it about cosine. The way that we do this is that if we're trying to find the inverse, what we do, the way we say inverse function is to say either arctan, arcsine, or sine of -1, right? That's just the way that we, that's two different ways to write inverse of sine. This looks like the buttons on our calculator, right? What we do to put this limit on it is we just substitute in an uppercase letter. And the same thing here, we just substitute in an uppercase letter. When you see that uppercase letter, this implies the limits. Okay, so if you see the lowercase versions of this word, you go, oh man, I have to find an infinite number, right, of spins that all will come and end at this proper point. But if you see the uppercase A and the uppercase S, and this is usually the one that John prefers to use, that means, no, you don't have to list them all, just list the ones that are within the limit. All right, so these are your friends. When you see those capital letters, you go, whew, happy days. And the same thing over here, or I forgot to write it. If you write arc cosine or cosine of -1, then that's drama because that means you have to account for all the spins. So again, we use that uppercase letter on either one of them. And that uppercase letter implies the limits. And this isn't a big deal because we're always going to put the limits on. We're not really going to talk about this at all. All right, now I'll go on and talk about tangent. And before we flip to that, let's just look right here. Tangent, we can see, is positive here. And what we do is we take this one. Tangent, we could go either way, right? Because tangent is also, wait, I think I did it wrong. I did. Not here. I always do that. I have such a mental block on it. We don't want this value. Tangent is going to be, no, this is right. I'm sorry. I did it once wrong a couple years ago, and now I'm always paranoid I'm going to do it wrong. It's like this. Tangent and sine ride together. So tangent is the first and the fourth quadrant, and it goes from 90 to -90. Okay, and I guess probably the better way to write that would be -90 to +90. That's a little bit more in order, and let's fix this one. It's from -90 to +90, okay? But what I want you to see is that tangent and sine are the first and the fourth quadrants, and cosine is the little freak child that has to go over to the second quadrant instead. All right, so that's the way we write the limits on these. Let me go back and talk about tangent and not be paranoid about making the same mistakes. Inverse tangent. We'll use our very same triangle so that that's not confusing us by changing. This is 60 degrees. 1, 2, square root of 3. So if we wanted to find the regular function, we would say, okay, the tangent of 60 degrees equals what? And then we would figure out tangent is over Arthur. So it's opposite over adjacent, square root of 3 over 1. Okay? If we want to find the inverse function, that's the answer to our question, right? We know the degrees and we find the decimal, or in this case, fraction. With an inverse function, we don't know the degrees. So we use theta to stand for the variable, and we're saying what is the angle whose tangent would be square root of 3 over 1. And we don't want to have to spin, right? We know that theta could be 60 degrees, and we've already done this, so we know that it also could be 360 plus 60, which is 420, or we could spin around twice and it would be 720 plus 60, which is 780. And we could keep going, right? Just spinning infinitely. There's 1, there's 2, there's the third one, right? We don't want to do that. So we're gonna put the limits on. Our inverse, place a limit on the angles used. For inverse tangent. And like I said, they will be from -90 to +90. Okay, so, and let's go back to our chart where we wrote them all. right? So sine and tangent have a limit that looks exactly the same. Cosine is the little goofball that goes over here. It goes from 0 to 180, right? Because this is 180. It takes these two quadrants. Sine and tangent both go this way, all right? We're going to do this for a long time. You'll get used to it. And I just wanted to say this as well. When we're writing out the problems and when we want to find the inverse tangent, we could do this thing, the arctan or the tangent of -1, but that would imply show me all of the different angles. We don't want that, so we use this uppercase to imply, no, just give me the ones in our limits. This probably seems wildly confusing. We're gonna do this a lot and you will get used to it. And every time you see that uppercase, you will smile because it makes your life way easier. All right, let's practice a few examples here. And you'll see how we can use this and it's actually quite reasonable. This is one of those things that sounds so hard when you're explaining it all. And you should see how John explains it in the book. It's murder. It's so confusing looking in the book. Okay. Example 32.3. It says evaluate arc sine square root of 2 over 2. Okay, so what John's saying is find me an angle whose sine is square root of 2 over 2, right? And we remember that this is opposite over hypotenuse. That will work, right? So we know what this is, and this tells us that we don't have to find a whole bunch of angles. We can limit it to just the two quadrants for sine, and we'll remind you of which those are in just a minute. Sine goes from -90 to +90, right? It's first and fourth quadrant. That's the sine limit. Okay, and I got that off that chart we made way back at the first page of our notes. All right, so that's good news. I don't have to worry about a bunch of spinning around. Now what I have to do is figure out what triangle would give me a ratio of opposite to hypotenuse that would look something like that. Now, here's a fun thing. We can be pretty sure that we know for sure, we don't need our calculators for these, it's gonna be either the 30, 60, 90 triangle or the 45, 45, 90 triangle. Now, I see square root of 2 and I go, okay, well that must be the 45, 45, 90 triangle, but I'm a little confused because this doesn't look like the opposite side or the hypotenuse. Let's draw the 45, 45, 90 triangle and see if we can figure it out. That ratio looks a little off, doesn't it? It's just the square root of 2 that's making me think, oh, well, 1 square root of 2, right? 45 degrees. So, in what world would from what I can tell, it would be the sine of 45 degrees, right? That would be the right angle, but that equals 1 over the square root of 2. This is not the same as this. But then I go, oh, wait a minute. What if we take 1 over the square root of 2 and rationalize the denominator? Look what we get. Square root of 2 over 2. Now it's exactly the same as this. So sometimes we'll be given a value for the inverse function, and we have to kind of de-rationalize it. So what we could have done up here, it's perfectly fine to do this, just to go, wait, that's close, it doesn't look quite right. Let me write it the way I see it based on the picture, and then let me play with it and see if I can make it look like that. The other thing you could do is start with this and go, let's try to put the radical back into the bottom. So what you do is multiply it by square root of 2 over square root of 2. This gives me a 2 on the top. This gives me 2 times the square root of 2 on the bottom, right? Those would cancel and I would get 1 over the square root of 2. And that's another way to make them match. So you can either work ahead of time to try to put this back into its original form, or you can just work with what you know and then play around and see if you can get them to match. Okay, so we know that a 45-degree angle is going to work, right? So we know that the arc sine of this is going to be 45 degrees. But what about the negative side? Couldn't we also draw a triangle that goes like this? That would also be 1 square root of 2? And couldn't we say that the sine of, let's see, that would be like negative 45 degrees, right? Let's just write it like that. The sine of negative 45 degrees. Wouldn't that also be 1 over the square root of 2? And the answer is no, because what this would be, the sine of minus 45 degrees, would be minus 1 over the square root of 2, because sine in the fourth quadrant is negative, okay? So we can rule out the negative side of this, and our answer is just 45 degrees. Make sense? I turned that into a big long thing, but in terms of your calculation, all you needed to do was look at this, figure out, well, which reference triangle is it going to be, and just make sure that you can make your ratio look back like John's. And then that was our answer, right? Okay, let's try another one. I wish I could see your faces right now, because that would help me know if you were like, yeah, this makes sense, it's fine. Or you're like, what in the world? 32.4, evaluate. This is how it's written. Arctan, okay, I like this. This tells me it's the inverse function of tangent, but I don't have to worry about a bunch of extra spins. I'm just limited to the 2 quadrants that are tangent. And I look back at my other little chart and I know, oh, this is going to be between, this should be a minus sign, right? It's going to be between negative 90 degrees and positive 90 degrees, or first and fourth quadrant. However, I didn't write all it down yet. I got so excited about that. Minus 1/3 times the square root of 3. Okay, once again, I think this looks a little screwy. I don't know what to think about that, but I do know if it's got a square root of 3, it's probably, it's a 30, 60, 90 triangle, and I just have to orient it properly, right? So I know that the tangent of some number is going to be equal to minus square root of 3 over 3, right? I'm just pushing those together. John's just trying to trick us by writing it weird. And based on the confidence I had last time, I'm just going to go ahead and draw my triangle. So this is over Arthur. So let's see, that means the opposite side. I am going to go ahead and fix it, because I don't want to confuse us with something else. I'm going to multiply this times the square root of 3 over the square root of 3 in the attempt to get that radical back in the bottom. This will become 3 over 3 times the square root of 3, and this will become 1 over the square root of 3. Okay, so this needs to be my opposite side, and this needs to be my adjacent side. So I'm going to draw it in 2 quadrants, and I know that it must be a 30 degree, right? Because that would be 1, 2, and this would be square root of 3, and then when I find my tangent, I want it to be in this order. I want the opposite to be 1, and I want the adjacent to be square root of 3. It's perfect, right? The only problem is it needs to be negative. So this 30-degree angle is not going to work, because that's positive. So my only other choice is to go down here and imagine this angle, which is 2, right? It's still gonna have the tangent I want because from here the opposite is 1 and the adjacent is square root of 3, but tangent is negative in the 4th quarter and that's what I want. So that means that the size of this angle must be, I could write it as negative 30 degrees or 330 degrees. Right? And John agrees. This is the way John writes the problem, but I kind of like to rewrite it like this. I say, I know this is going to be the decimal or fraction number. I don't know the degrees. Remember, with an inverse function, it always means I know the decimal or fraction. I don't know the degrees. So I kind of like to rewrite it. This and this mean the same thing. This just looks more familiar and friendly to me. Okay, this is correct. John used the negative value. I wrote the positive one as well. Okay, that is number 4. Let's go on to number 5. And there are 6 in all, so we're almost done. You survived. Well, if you don't die in the next few minutes, right? 5. This time, oh my gosh, this problem looks crazy. We're supposed to find the cosine of the angle Okay, John says, find the cosine of the angle whose tangent is minus 3 over 5. So we have to figure out how many degrees this angle would be, and then we need to figure out what the cosine of that same angle would be. This is more complicated than what we've done. But just like any other problem, we're going to start in the middle. And so I'm thankful for the A. That means I know I have limits. And I'm going to rewrite this in a way that I like it. The tangent of some angle is going to be equal to minus 3 over 5. This tells me it's in the 4th quadrant, because it's minus, right? But I don't recognize these numbers as coming from either one of our triangles. So, right, it's not a 30, 60, 90, and it's not a 45, 45, 90. I don't know what the heck that is. But what I'm going to do is, in good faith, I'm just going to draw it because I know this is over Arthur. So I know that I'm going to have a triangle. I know it's going to be 4th quarter. I'm just guessing on the size of it. The opposite side is going to be 3, and the adjacent side is going to be 5. Okay? I don't know how many degrees this angle is. And I'm frustrated because that is what I'm supposed to be finding, but don't worry, it's going to work out fine. Now, I don't know how to find that degrees without using a calculator, and we're not doing that. But I can figure this out. This is the hypotenuse, right? And I know I can find that using Pythagorean. So I'm going to say that the hypotenuse is equal to the square root of 5 squared plus 3 squared, right? That's just Pythagorean set up to solve. Pythagorean, let's see, this would be 25. Do I have the numbers right? No, it's 2 and 3. My bad. This should be a 2, and this should be a 3. Then this should be a 2, and this should be a 3. Let's double check and make sure that's right. 2 is the opposite side, 3 is the adjacent. Okay, so this becomes, we'll make this one into the 2. Sorry, I just copied the problem wrong. My bad. Okay, so 2 squared, 3 squared, add them up, take the square root. 2 squared is 4, 3 squared is 9. Oh, I'm looking at the wrong problem. Oh my gosh, you guys, I'm gonna start over. I was doing fine. It was the 3 and the 5, and then I got confused and looked at the wrong problem and copied that number instead. So, oh my gosh, let's start all over again. I'm sorry. As if this isn't taking long enough, I'm making it even longer. What? Go back to where we were. All of this was right. Okay, so what we're saying is we want to find what angle will give us a tangent of minus 3 over 5. We know this has to be the fourth quadrant because it's a minus tangent, and we know that tangent ranges from minus 90 to plus 90 or vice versa in the first and fourth quadrants, right? We don't recognize this as being from a reference triangle, so we're just going to fake it. Here's a triangle. This is over Arthur, so this side has to be 3, and this side has to be 5. We don't know what the hypotenuse is, but we can calculate it using this information. The hypotenuse is equal to the square root of 5 squared plus 3 squared. 5 squared is 25, 3 squared is 9. So h equals the square root of 34. We don't have to worry about the negative square root because this isn't a negative number. Okay, so this equals the square root of 34. Now, we still don't know, without a calculator, what this angle size is. But here's the thing. It doesn't matter because John isn't asking us for the angle size. He's asking us to find the cosine of that same angle. So we've got all that information set up right here. This is the angle. We can just call it theta. We don't know what it is. But cosine equals a hold, right? So the cosine of the same angle equals the adjacent 5 over the square root of 34, the hypotenuse. Does that make sense? We never did figure out how many degrees this was, but we don't care because John didn't ask us for an answer of degrees. He asked us to find the cosine of the same angle. And we were able to do that. And all we have to do is rationalize this now. And so the answer is 5 times the square root of 34 over 34. That's the cosine of the triangle that we found using this information. Isn't that crazy? That's kind of a weird thing. Okay, and now we have the last one, which you've already seen half of it because I tangled them together in a completely bonkers attempt to do math. But now I'll be fine. 32.6, ready? This one's similar. We're supposed to find the sine of the angle whose cosine is 2 over 3. All right, so we know that we're limiting. We can look at this another way. We can say the cosine of some angle equals 2 over 3. Again, we don't have a reference triangle that's going to give us those as sides. This would be a hold, right? So we're just going to have to make our own triangle. It's positive and it's cosine, so we know it's in the first quadrant. And again, we don't know how big this angle is. I'll just call it theta. But we do know that the adjacent side is 2 and the hypotenuse is 3. Okay? So we just have to be careful how we put these signs on these lengths on our triangle, and we just follow the pattern of the function that we're talking about. All right, so now we need to find this one, which I'm going to call the opposite side. I'm going to call it OPP so that I don't get confused. And I know that I can use Pythagorean, so 3 squared equals the square root of 2 squared plus OPP squared. This is 9. This is one where the shortcut version isn't going to help us. So let's write it the other way. It's going to be 2 squared plus OPP squared equals 3 squared. This will work better for this, right? This is 4. We subtract 4 from both sides. OPP squared equals 5, and then we take the square root. So the opposite is equal to square root of 5. Now we have all 3 sides. We still don't know the angle, but we realize John doesn't need us to know the angle. He needs us to find the sine of that same angle. So we go, okay, cool. Sine of the same angle. Sine is Oscar had, so it's opposite, square root of 5 over hypotenuse 3. So our final answer is square root of 5 over 3. Is that a little bit head-blowing? Normally we use inverse trig functions to find the degrees of the angle, but sometimes we have these problems that take us a step farther and say, don't worry about what the angle is, just draw the triangle, and then you can use those numbers from the same triangle to find another function. We never did figure out what the angle was because we didn't use our calculators, but it's okay, we didn't need that. We needed to find the sides for this new ratio, and it all worked out. And in this case, we know that it's only first quadrant. We don't have to worry about any negative values because this is positive, right? So it's just the one answer. Guess what? We're done. We're done with this lesson. We're going to be fooling around with inverse trig functions a whole bunch. So don't worry, they'll settle in and you'll get really fast at them. I do want to say this. This whole thing we did way back here in the beginning about the inverse functions period and the way that you can take one function and then find its inverse by following these 2 steps. This shows up a lot on placement tests and such. So put these notes, we won't remember it because we don't do a whole lot with this. So that's why they've, you know, the people who write those tests are kind of dirty dogs, I'll just say. They try to trick you and it's not nice. But put these notes somewhere where you'll find them where when you're studying someday to go to Edmonds College or take an SAT or some such thing. So put them somewhere where you can find them later and remind yourself, oh yeah, this is something I do want to try and remember. All right, the inverse trig functions, don't worry. We're going to spend lots of time on those. I'm done. I think that was more than enough, don't you? Would you like me to make some more mistakes and confuse you? I know. Okay, 32 is over. Oh, let me just show you. Look. These 2 lessons are done. We only have 4 weeks left before Christmas, and somewhere in here is Thanksgiving. I want to, first of all, remind you that the midterm is coming, and memorizing all this stuff I have given you is going to be a bit of a chore, so start working on it now. Make sure you're memorizing as you're doing the homework. Number 2 is good news. I'm going to tell you that somewhere here around Thanksgiving, I am going to give you a reprieve in some way on some homework. I'm going to lighten your load for Thanksgiving weekend in some way. I'm still planning it. I'll let you know when we get there, but I just want you to know your hard work is going to be rewarded, and I'm going to give you a little bit of a break for the holiday. Okay, I'm done. Thank you. Goodbye.